All right, let's get right into it. The entire digital world, your phone, your computer, all of it, runs on a really common material that we've taught how to be smart. And the secret to making it smart? It's a tiny, perfectly controlled flaw. Today, we're going to break down how we create the perfect imperfection.
So, how in the world do you get from this?
The element silicon? It's the main ingredient in sand and quartz, and it's literally one of the most abundant things in the Earth's crust.
To this? The intricate microscopic brain, the microchip, that powers pretty much every single piece of technology we use today. Well, the answer is kind of wild when you think about it. We have to make it imperfect, on purpose. The whole secret is learning how to control those flaws with unbelievable precision. Okay, so first things first, we gotta understand what we're starting with. Perfectly pure silicon. It's an amazing, stable material, but when it comes to electricity, it's pretty stubborn. You see, in its pure crystal form, every silicon atom has 4 outer electrons, and each one of those shares an electron with a neighbor, forming a super strong bond. Think of it like a massive grid of people all holding hands with 4 other people. Everything is locked down tight. There are no free electrons to move around, which means pure silicon is actually a terrible conductor. For all intents and purposes, it's an insulator. So to make it do what we want, we have to mess up that perfection a little bit. And this, right here, is where the magic happens. It's a process called doping. Doping is just the fancy word for intentionally introducing super tiny amounts of other elements, what we call impurities, into that silicon crystal. Now, this isn't about sloppy manufacturing. This is a highly controlled, incredibly precise process that completely changes how silicon interacts with electricity. And when I say tiny amounts, I really mean it. For what we call light doping, you might be adding just one single impurity atom for every 100 million silicon atoms. Even heavy doping is only about one impurity for every 10,000 silicon atoms. It's that level of precision that lets us build the complex stuff inside a chip. Okay, so how does this actually work? Let's look at the first type of doping, which creates something called a p-type semiconductor. And the P, that stands for positive.
To pull this off, we use something called an acceptor atom. A classic example is boron. Now, boron is in group 3 on the periodic table, which just means it has only 3 electrons in its outer shell to share, not 4 like silicon does.
So, what happens when we sneak a boron atom into the silicon grid? Well, it tries to fit in. 3 of its electrons form perfect bonds with its silicon neighbors. But where that 4th bond is supposed to be, there's an empty spot. Nothing. That unsatisfied bond is what we call a hole. Now, here's the really cool part. This hole isn't just empty space. It actually behaves as if it has a positive charge. And it can move. An electron from a neighboring atom can jump into the hole, filling it. But in doing so, it leaves a new hole where it used to be. This creates a chain reaction, allowing these holes to move through the crystal, acting just like a mobile positive charge and carrying an electric current. Okay, so that's p-type, where we create positive charge carriers. Now let's look at its counterpart, n-type silicon. And you can probably guess the N here stands for negative. To make n-type silicon, we use an element from group 5, like phosphorus, which has 5 electrons to share. So when a phosphorus atom takes a silicon atom spot, 4 of its electrons form those nice, perfect bonds with the neighbors. But that 5th electron, it's just left over. It's not needed for bonding, so it's totally free to roam around the crystal lattice as a negative charge carrier. So let's just recap, because this is the key. With p-type doping, we use an acceptor atom like boron to create a shortage of electrons, which gives us mobile positive holes. With n-type doping, we use a donor atom like phosphorus to create a surplus of electrons, giving us free negative electrons. 2 sides of the same coin.
So now we have our 2 custom materials, one that's rich in positive holes and another that's rich in negative electrons. On their own, they're pretty interesting, but when you put them together, that's when you change the world.
The p-n junction, it's simply the boundary where a p-type region meets an n-type region, is the absolute most fundamental building block in all of electronics. This junction is like a one-way street for electricity, which is the whole idea behind a diode. And when you start combining these junctions, you get transistors, which are basically tiny little switches. Billions of these switches, flipping on and off, make up the logic gates inside the microchip in your device. This is literally what makes it think. But the science is far from settled. At the cutting edge, especially in high-power electronics, things get really complicated. Imagine you flip a switch, but not all the lights in the room turn on at the exact same time. A similar thing can happen here. Not all of those impurity atoms activate and release their charge carrier instantly. This creates a temporary imbalance that can cause huge problems in really fast or powerful devices.
And this is a massive challenge because the time it takes for these impurities to get to work is incredibly sensitive to temperature. As our devices run faster, they get hotter, and engineers have to predict and manage these tiny microscopic delays to stop them from failing. It's a constant race to perfectly control these so-called imperfections. So just think about it. From a simple, abundant material, we create logic and intelligence just by introducing these microscopic, perfectly placed flaws. The entire digital world is built on this foundation of engineered imperfection, which really just leaves you with one final thought. What new properties are just waiting for us to unlock? What will the next perfect imperfection make possible?